Hello, everybody, and welcome to this next edition of Behind Every Drug, There is a Story, sharing progress in cancer care. Today, we're deeply honored to have Professor Takmak with us, and I can't wait for all of you to have the opportunity to hear his incredible story. Professor Takmak will also give you an overview of his career, but I would just like to give you a snapshot of his current post and what he does. Dr. Takmak is the director of the Campbell Family Institute for Breast Cancer Research in the Department of Medical Biophysics at the Princess Margaret Cancer Center, and he also holds a post at the Cancer for Oncology and Immunology at the University of Hong Kong. Just some highlights from his career. He is the one who discovered the T-cell receptor, the function of CTLA-4, has started Agios Therapeutics that gave us the IDH1 inhibitor, and has done so much more in his career and scientific and medical development that I can't wait to have him share the story himself. So without further ado, welcome to this edition of SPCC, Beyond Every Drug, There is a Story. And I would like to invite you, for our audience, to provide a story of the arc of your career. How did it start, and what would you say were those highlights that bring us current?
Thank you very much, Aleksandra. I'm a little bit kind of shy, or maybe overwhelmed to receive this introduction. My life is actually pretty simple. I grew up in Hong Kong and then moved to America when I was a teenager. I ended up at the University of Wisconsin with the intention of doing chemical engineering, and which the University of Wisconsin was and still very prominent in. But I quickly discovered that engineering wasn't for me. It's a pretty kind of intense and repetitive kind of work. And I realized that my mind was more around wandering into the woods and looking for something that was different. So I left the Department of Chemical Engineering and transferred to the biochemistry at the University of Wisconsin, which at that time was very prominent because there were a lot of fundamental discoveries there, by a lot of very prominent professors. For example, vitamin D was made by UV light going through milk, and that actually made the University of Wisconsin a lot of money and allowed a lot of us to do very kind of like pioneering biochemistry. I entered the laboratory of Professor Roland Rickert, and he was a very precise virologist, titrated everything very carefully, and where I actually learned that science has to be methodological, behind which, of course, I knew concepts which I very, very much enjoyed, finding new things that I didn't know before, and sometimes nobody knew before. So I finished the University of Wisconsin and went to Canada. I worked for a very prominent hematologist by the name of Ernest McCullough in Toronto. And he and James Till are credited for discovering the hematopoietic stem cells, which I find very fascinating because the hematopoietic system and the liver are the only two organs that can regenerate. They know when to start and they know when to stop. And to me, that is fascinating. And from there, I learned a lot about how to think very freely. And then that time, around 1980, molecular biology was coming in, and everybody has to learn molecular biology in order to get into the next stage of scientific frontiers. And I went back to the University of Wisconsin and worked with Howard Temin and learned molecular biology of viruses. And then I went back to Toronto at the Princess Margaret Hospital, and I received a position. And at that time, one of the biggest mystery of, at least the immunology, hematology arena or field was what was the T-cell receptor? How does our body actually tells the difference between self, part of your kidney, your liver, your lung, and non-self, virus, bacteria, parasite, or maybe even cancer. And so that's because of the technology that I have learned in virology of subtracting different viruses to identify molecular subtraction by hybridization, to identify which viruses have what genes, thereby allowing them to cause what diseases. We naively and bravely and went into the field of immunology and said, why don't we subtract T-cell genes from B-cell genes, assuming the T-cell receptor is T-cell specific, which was not considered the case at that time. The paradigm was the T-cell receptor is very similar to immunoglobulin. So luckily, two kind of reckless laboratories, ours in Toronto and Mark Davis' lab at Stanford, at the same time stumbled onto the T-cell receptor, and that's how it all got started.
How incredible. And I'm hearing you really speak to how every single moment in your career and every single position that you held, every single lab where you worked, all of the discoveries and the techniques that you've learned were really priming the way to this ultimate discovery of the T-cell receptor. And that all of that was needed for you to discover the T-cell receptor.
It was an amazing, kind of like the arrangement of the stars. It was too impossible. I guess I didn't appreciate how important it was when I went to a very prominent Ivy League university, and the chairman of the department said that 18 labs in his own department alone were looking for the T-cell receptor. And how do two 30-year-old innocent, reckless young scientists who just started their lab at Stanford and in Toronto kind of came upon it with exactly the same technology, which was at that time just being developed because 4 years ago, Stalin, Varmus, Bishop, and Vogt did the subtraction between SARC and avian leukosis virus, and then isolated the SARC gene and received the Nobel Prize. for discovering oncogene. And just a few years later, two labs applied that technology. Had to be much more kind of technically challenging, because in one case, in the SARC minus avian leukosis virus, there's 4 genes minus 3 genes. But in the case of T cell receptors identification, it was T cell, which could be, I don't know, 8,000 genes minus 7,900. And then search among this whole, well, we got 1,500 genes out of it, and search amount which one could be the T cell receptor. I know someone has to be crazy to think that that would actually work.
Incredible. And you need to have that level of, call it craziness and faith combined, but that scientific curiosity and belief that it's possible, and that it's worth it.
Yeah, I was also very lucky, because I think it's not just being kind of like reckless and thinking out of the box. I also had I applied for a grant to do this, and I was told by the granting agency that no Canadians should be looking for the T cell receptor. Wow. So it was rejected, but my boss, Ernest McCullough, who I owe like everything to, and of course the postdoc, a Japanese 25-year-old medical doctor from Japan, Yusuke Yanagi, who was just here last week. He, and McCullough got me the money and said, forget what the granting agency say. He was very upset, because that implies Canada has no place into looking into things that are too out of the box, and perhaps, science is about taking chances. Science is about challenging the paradigm. But he got me the money, which was $30,000. And we did the subtraction, and I mean, how lucky can you think? I'm thinking, looking back, it just it's crazy.
It's really fascinating and such an incredible journey. When you speak about this today, I want to ask you 2 questions. One, was there a moment in this process when you knew, it was like, this is it, here it is, we found it? And then as you speak about all of this today, from this perspective and everything else that you've achieved and have discovered in your career and gifted the science and medicine with, is there any emotion that's coming up?
The emotion is still, after 40 years, it's still a sense of disbelief that it could. It was really interesting, because this year in June, I had a drink in a restaurant with Mark Davis. And for 40 years, I had always thought that he knew what he was looking for, and he did what he had to do, and he got it. Now, when I was told no Canadian should be looking for the T cell receptor, which I still find very insulting, I had to talk myself and a potential funder that I would be looking for anything that's T cell specific. And in retrospect, we cloned LCK, CD4, CD3 because they were T cell specific.
Wow.
So I had to tell myself that. And I thought that Mark Davis, who by the way, he's even younger than me by 2 years,
Mm-hmm.
that he knew that only T cell receptor was what he wanted, and without which he wouldn't bother. He told me after a couple of drinks that, he was also very practical. He
Mm-hmm.
just wanted something that was T cell specific, which, of course, there are dozens of genes that are T cell specific that are, that play important roles in T cell immunology.
Absolutely. And your discovery really has shaped the science thereafter, immunology thereafter, at the very least, because there's sort of that pre-discovery of T cell receptor and everything that happened before, because you've really set the basis and laid the grounds for so many drugs to then be developed, which we're reaping the benefits of today, not just in oncology, but across disease states. And as your career went along, some other highlights would then be the CTLA-4 came into play. Would you tell us a little bit about how that discovery happened?
Well, when I was a virologist, I was in my early 30s. Our lab stumbled onto the T cell receptor, and then of course, just before then, there were 25 years of immunology talking about T cells, and of course, I never understood a single word of it, because many of those experiments and many of those concepts were based on kind of mechanisms of T cell recognition, which was not really well-founded. And so I was totally confused. I came from the field of virology. I only had to deal with 3 genes or 2 or 1. And then all of a sudden people talking, like the universe was in war, and everybody talks a different story. And I was very lucky because here in Toronto, there is Janet Rosent, who was one of the pioneers of developing genetically modified mice. And well, not exactly, but she was part of the heritage out of Cambridge in England on how embryonic stem cells develop. And then I met Klaus Rajewski, a very prominent B-cell immunologist in Cologne, Germany. And we went out to dinner in a Spanish restaurant. And I said, hey, Klaus, I know you. He's about 10 years older than me. And I was just, young 30s. And I say, Klaus, it's just, I understand how I can ever learn immunology. And he said, no, don't worry. The techniques of making genetically modified mice is coming through. We just have to work out the techniques, because the background of embryonic stem cells is there. And so together we collaborated, we shook hands and say, if we do it, you take T cells, that was me. I take T cells, B cells, that was him. And then we will, try to clarify some of the kind of confusing immunological concepts. In 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 those days, one of the kind of like derogatory terms that you say about someone. For example, someone give a talk and you have no idea what he's talking about, she's talking about, and it's just all made up because there were no concept, there were no genes, and the immune system can do everything under the sun, and you would just say, "Yeah, don't worry, it's all immunotalk." So, so we decided that with genetically modified mice, then if you knock out gene number 4528 and there's no thumbs, then that gene makes thumbs. That's how simple-minded I was. So the two of us worked together, and in fact, we were not number one. The two of us made the number 2 and number 3 mice in the world. I made CD8 knockout, and he made immunoglobulin knockout, IgM knockout, and then then it's clear. You knock out this, and something happened. Knock out this, something happened. And then in 1995, Paul Waterhouse in the lab came in and said, all his mice died at 2 to 3 weeks. I said, what mouse? Oh, CTLA4. I said, no, it couldn't be. It's an immunology goal. Because we made CD28, and CTLA4 was supposed to be the same as CD28. It's supposed to be 2 co-stimulatory molecules. And then we opened up the mouse. Pop! All the lymph nodes popped out.
Wow.
Yeah, 10% of the weight of the mouse were T cells. And then I said, oh my gosh, it's a break.
Incredible.
We never knew that the immune system has a break, right?
Yes.
And then we published that in Science in 1995. And I met one of my best friends, Jim Ellison, and he said, oh, well, it's going to cure cancer. I said, don't be stupid. And then he made an antibody, blocks CTLA4, and a paper in 1996, in Science also, showed that if you add antibody CTLA4, it wiped out the tumors. And then he went on and coordinated clinical trials, and that, of course, was brilliant. That was the beginning of the 4th pillar of cancer treatment, immunotherapy.
Exactly. That gave us ipilimumab in 2011, if I'm not mistaken, with the approval.
Absolutely, yeah.
Incredible. When you think back now, that really starting from your discovery of the T cell receptor, which then led to really studying immunology in such great depth and understanding what all of these receptors and co-stimulatory molecules were doing through knockout mice, did you ever once think that you would, in effect, be completely transforming the therapeutic landscape?
No. In 1987, I was in Israel in a place called Ein Gedi. At that time, George Klein runs these summer courses in Ein Gedi. It's a kibbutz. I don't know what you know about a kibbutz. It's a very cool place. It's just all so unreal. You walk into every store, you can take anything you want. You walk into restaurants, you can eat without pay. It's kind of like, a commune of some kind. And George Klein, at that time at Karolinska Institute in Stockholm, and Eva Klein, his wife, they run these summer courses.
Mhm.
And somehow I got kind of adopted by him. And so I get to go to iGetty. And I met this professor by the name of Zelig Ishar, Eshhar, Zelig Ishar, in iGetty. And he said, Tak, T cell receptor, it's too complicated. It's got a recognized peptide, HRA, and he said, can I use your T cell receptor? And instead of having the T cell receptor outside, I put on an antibody on the outside. And I said, why? He said, what do we call it? It's called chimeric T cell receptor, CAR-T. I said, wow, nice. Go ahead.
Wow.
I don't know what you're doing. Do whatever you're doing. And in 1989, he published a paper in PNAS that CAR-T can kill B cells. And from there on, it's now, 50,000 patients have been treated, and 40 to 45% of the lymphoma patients have been cured. And for ALL, it's like even higher percentage. I mean, cured is probably not the word, but if you look at the Kaplan-Meier curve, they, after about 3 years, they flatten.
Yes.
And it looks quite stunning.
It's quite remarkable survival now that can be achieved thanks to CAR T cells.
Yeah, of course, Michelle Satterline and Carl June did a lot to improve it, and now, it's been approved. A T cell receptor, CAR TCR2, is now been approved for GP100, for uveal melanoma, I think MAGE-A4 for synovial sarcoma, and NYESO1 just came out. Clinical trial looks pretty good. So it's very satisfying.
Truly a complete transformation of therapeutic landscape thanks to your discoveries.
Well, no, not me. There are hundreds of people there,
yes. And you were a part of that, and a big part from what I'm hearing.
Now, I think I look at myself as a pot of soil. And, I either plant the seeds or seeds fall on. And if they're the right seeds, given the right soil, they blossom. If not, they.
And I think that's such a beautiful way of looking at it, and also beautiful advice for everyone who's in research and science and drug development, and just in general in science and medicine. It's a beautiful metaphor for this work that we do.
Well, I mean, you know very well. You have yourself have been very, achieved.
Thank you. Thank you. And as we talk about seeds and soil and the right environment, and also the right seeds being planted in the right environment, I'm curious if there is anything that you would say was important in your own origin story, in your upbringing. You were born in China. I read somewhere that your parents were silk merchants. Is that correct? And that they really wanted you to be a doctor, but then you really carved your path. Was there something in your upbringing and really in that origin story that planted the seed for your development as it happened in your professional sense?
Well, I have to just kind of go back. So yeah, my grandparents, my great grandparents were considered very, very wealthy. But when the communists took over, you know, we went to Hong Kong, and then, of course, you know, lost everything. Then we had to get started. I went to a Jesuit school, Irish Jesuit. In fact, last month I went back to Ireland to visit the graves of the priest that brought me up in Dublin.
Wow.
You know, felt very grateful, touched, and it was a very eventful trip for me to go find the graves and, you know, pay my respects. Then, of course, we moved to America, and all that kind of left behind. I don't know how you could. At one point, I was actually in the seminary, but anyway, I mean, I told you the story. My mother wanted me to be a doctor, and I was reasonably good at mathematics and chemistry, so I wanted to be chemical engineering. And because I learned my lesson, it's not for me.
Mhm.
But then it was really Roland Rickert who taught me about science. I mean, I went to the lab to get a job for washing pipettes because I needed money to pay for my tuition. But after I washed all my test tubes, then I said, I need more money. I don't have any more. He said, well, do experiments. When you finish doing experiments, which I will pay you $1.25.
Mhm.
He only paid me $1 to wash dishes.
Mhm.
And then you can wash your dishes. And the more experiments you do, the more dishes you can
If you
wash.
wash.
And so you get to be, you know, kind of double dip. That's how I managed to go through and pay enough money. I was going to go to medical school,
Mhm.
and I actually never showed up because
Mhm.
I enjoy science so much.
Amazing. And what a gift to the entire world that you do. Really.
No, don't ever say that. It's just,
Mhm.
I'm just that potter soil. I have to
Full of
give,
soil. Okay.
and you know, between McCullough,
Uh-huh.
who's a very free thinker, he's a clinician,
Uh-huh.
treating leukemia.
Mhm.
You know, in those days, of course, before real, yeah, it was just real poison, right?
Yes.
Um,
Yes.
I was shocked to find out, for example, the first chemotherapeutic agent was actually nitrogen mustard.
It
And I
was
thought,
discovered through an explosion on a boat.
aha, 1942, September the 2nd. No,
Exactly.
43,
Yes.
43, in Bari, Italy.
In Bari, Italy.
And the medical doctor was Stuart Alexander.
Yes. Yes.
So you know, he was very free thinking, uh, and then with Howard Tennant was so, I mean, there were no smiles. You have to call him Dr. Tennant,
Mhm.
and you have to have confessions every Friday morning, because Friday afternoon he has to go home
Uh-huh.
because he's Jewish. Friday morning, confession.
Mhm.
There is no other words to describe it. You know,
Okay.
bless me, Father, for I have sinned.
Mhm.
I didn't do this experiment. I didn't do this right.
Wow.
But to learn from him, I still think he's one of the smartest. Um, after all these years, there were experiments he told me. I still don't understand what he was thinking. And of course, you know, he has to be right.
And he had won the Nobel Prize for reverse transcriptase.
Yes,
Yes. Yeah.
yes.
Yeah. Yeah.
Yeah, that was also a very interesting story.
Right.
Right? Um,
And now, after your career, as you've just talked us through it and taken us through it, after actually journeyed through it with us, what are you now excited about? What are you working on now that potentially is again groundbreaking?
Well, two things. One
Uh-huh.
is TCRT.
Okay.
You know, um, I came across with my clinician friends
Mm-hmm.
that certain leukemias and lymphoma patients go into spontaneous remission in the midst of very, very severe diseases.
Uh-huh.
And I've collected 6 now. And it turned out that these patients with leukemias and lymphomas that went into spontaneous remission without treatment,
Mm-hmm.
in the middle of the family giving up, the tumor went away and stayed away for 10 years. A particular T cell receptor clone comes up.
Interesting.
And so that gives me encouragement to go after TCRT in a more random, not more random is probably the wrong word, in a less restricted way, like going after GP100 or human papillomavirus. This, I don't know, but it's true. There is no way. And these, whenever the T cell clone comes up,
Uh-huh.
the cancer cell disappears.
How
So,
interesting.
so that's one of my projects.
Okay.
And the second project is how the brain talks to the immune system,
Love
which I think is a completely new lens of looking at the immune system. It turned out that there were some German scientists back 170 years ago
Uh-huh.
were stimulating nerves and found the spleen moved.
Mm-hmm.
And 50 years later, people knew that they were stimulating vagal nerves,
Yes.
which make acetylcholine. And indeed, 100 years ago, scientists found acetylcholine in the spleen. And if you stimulate the nerve, you make acetylcholine. Everything was okay. But then, to my knowledge, nobody has found cholinergic nerve fibers in the spleen or in the liver for that matter.
Mm-hmm.
Instead, they only find sympathetic nerves, which make norepinephrine.
Mm-hmm.
So where's the acetylcholine comes from? So a very brilliant neurosurgeon, Kevin Tracy, at the Feinstein Institute in New York,
Mm-hmm.
he told me all this story, and I was shocked. And after a couple of years, we got together
Mm-hmm.
and we worked together and found out that it was the norepinephrine from the sympathetic nerves that activate the T cells to make acetylcholine. I said, okay, who cares? Well, brilliant American postdoc by the name of Maureen Cox came to my lab, and she deleted the gene acetylcholine transferase, which make acetylcholine, on T cells only. And now the mouse cannot clear virus.
Think.
So that paper was accepted without revision. All 3 reviewers said, they did it, they did it, they did it. They proved it, they proved it, they proved it. But now we found out that the neurotransmitter made by T cells is also required to control cancer in the liver cancer model.
Mhm.
and autoimmune diseases, and more and more and more and more. And so, again, the liver, to my knowledge, and two papers, one by Adori et al. In Science Advance, and another one from a Chinese group, Yang Jing from Peking, in cell metabolism.
Mhm.
They both said they looked and looked and looked for cholinergic fibers in the liver. They cannot find it. There is nothing there. And yet, lots of acetylcholine
Yes.
in there. And they pumped out by
Please.
T cells and B cells. And so we have now two papers in revision,
Uh-huh.
or three actually,
Mhm.
to show that without the T cells or the B cells making acetylcholine, the pathophysiology is completely different in many different indications. So it's not just us,
Mhm.
right? Tai Chi in Beijing, Tsinghua University
Mhm.
had a paper in Nature that showed that nicotinic 9 is needed for B cells to become plasma cells.
Mhm.
Susan Cat in San Diego in the Scripps, in a paper in Nature, showed that norepinephrine acting on T cells is required to prevent the T cells from getting exhausted. So that petty paradigm of the sympathetic nerves making norepinephrine to activate or inactivate the T cells to make acetylcholine.
Mhm.
That acetylcholine will now go to different parts of your organ and provide the acetylcholine that is needed for the various biological and physiological functions. Because acetylcholine is such short half-life. If every piece of furniture or book or thing in my room needs acetylcholine, I would not have enough cholinergic nerves to ever provide. So why not let the couriers, which are the T cells and the B cells, to take the message of the sympathetic nerves making norepinephrine,
Yeah.
then tells the T cells,
Uh-huh.
go, make acetylcholine, go
Yeah.
over there and
Deliver.
give the acetylcholine to
Yeah.
the macrophage, to
Incredible.
the hepatocytes,
Yes.
to any cell.
They receive the cue, they produce, they travel and drop the cargo.
Yeah. So acetylcholine, it's your whole body is soaked with acetylcholine esterase. So there's no way acetylcholine could even travel a millimeter or even a micrometer, I mean a meter. So the only way is to form a synapse. And so the T cells and the B cells get the cue from the sympathetic nerves.
Yes.
And say the stellate cells or the cholangiocytes or the hepatocytes needs acetylcholine now.
Mm-hmm.
Can you deliver it?
Yeah.
And the T cells go over
Yeah.
and deliver it to the
And deliver.
hepatocytes. Right.
This space of how our brain is connected to our nervous system, how it's a constant dialogue. It's not one directional, it's bidirectional, it's that information travels in both ways to inform both the brain and the nervous system, and then how that gets off balance in disease, and then how can we get it back on balance to have some therapeutic potential in that space. I feel that is really that next frontier. And it sounds like your work in this space is going to be really, really valuable there.
Yeah. Well, I come back to my two favorite organs, the liver, and I learned hematopoiesis from my colleagues and from McCullough. But that is, it can start, you can lethally irradiate a mouse and give it one hematopoietic stem cells, one. And the mouse will live. When the mouse completely is kind of like recovered, it stops with not one cell more, with not one cell less. How does it know how to do that? The liver is the same thing. You cut out 50% of the liver, they will regenerate. You cut out 90%, they won't. You cut out 70%, then there is the critical balance where multiple factors and genes and cells are coming to play in a very complicated Beethoven symphony. And then,
I love that word.
And it starts dum 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 dum, and then at the end it stops.
Yeah, I think that is such a beautiful place to complete our conversation today, because I love that metaphor again of the symphony and how it has a pace of its own and knows exactly sort of when it's time for which intensity. Yeah, and that's really the intelligence, that innate intelligence that lives within the human body.
And I will make one prediction.
Yes.
The nerves are calling the shots.
I absolutely love that. They are. Thank you so much for being with us today. It was truly such an honor to have this conversation with you.
No, I had so much fun.
Thank you. I'm so glad.
Thank you very much for this opportunity.
Absolutely. And thank you for everyone who's going to be tuning into this interview. You're going to have fun listening to this conversation. You're going to learn a lot. Please keep notes as you listen, maybe the second time around, because Professor Takmak really references a lot of his own papers, a lot of papers from his colleagues and co-workers, some from before, some very, very recent. And I'm sure that if you go and take a look at that literature, you're going to further be enriched a lot in your knowledge and in your career. So again, thank you so much. It was such a privilege.
Thank you very much. I really enjoyed it.
Thank you. Amazing.